We are going to talk about rational functions extended in this lesson. And before we do our live Class Connect session, I wanted to go ahead and do this video on Tuesday so that you would have an opportunity to have some information before we did it totally from scratch. First thing that we're going to talk about is finding the horizontal asymptote of rational functions. To do that, you are looking at the original problem. You do nothing to it except just look at it. And what you're looking at are the degrees of the numerator and the denominator. The horizontal asymptote is determined by the largest degree, is what you're basically looking at. And I'm going to talk about this in three different ways. The first way that we're going to look at it is using an acronym, and the acronym that we're going to be talking about is BOBO. What BOBO stands for is biggest on bottom zero. What that means is if the largest degree is on the bottom of that rational function in the denominator, then your horizontal asymptote is always going to be y is equal to 0. Second type is BOTN, B-O-T-N. That is an acronym that stands for biggest on top, none. So that is saying that if the largest degree is on top, the numerator has the larger degree, there is no horizontal asymptote. And the third is not really an acronym, it's just saying that if we're going to call it same, and that means that the numerator and the denominator have the same degrees. When that takes place, to get your horizontal asymptote, what you're going to do is to take the leading coefficient on top, the number in front of the largest degree on top, and you're going to divide it by the leading coefficient on the bottom and simplify, and that would give you your horizontal asymptote. All right, examples of this that I'm giving, the first one is dealing when the degrees are the same. If we look at the rational function, on top we have the trinomial x squared plus 7x plus 2. The degree of that trinomial is 2. On the bottom, we have x squared minus 25. The degree of that is also going to be 2. So to get the horizontal asymptote, we are going to take the leading coefficients, 1 divided by 1, which is equal to 1, and my horizontal asymptote would be y is equal to 1. Second problem is an example of BOBO. Biggest on bottom 0. When I look at the degrees, the degree of on top, the numerator is x to the first power. The degree on the bottom is 2. Since 2 is bigger than 1, we have a situation of BOBO, and the horizontal asymptote is always going to be y is equal to 0. The last problem is an example of BOTN, biggest on top, none. When you have the largest degree, which is 2, on top, because the degree on the bottom is 1, there is going to be no horizontal asymptote. The horizontal asymptote, once you find it, determines the range of the function. If you have a situation to where you have the biggest on the bottom, 0, and your asymptote is y equals 0, then your range is going to go from negative infinity to 0, union 0 to infinity. A situation of BOTN, there was no horizontal asymptote, which means that there are going to be no restrictions on the range of that function, and the range is going to be from negative infinity to infinity. You also might see that written as just the set of real numbers. Okay? And when we have the situation of same, The coefficient on top is divided by the coefficient on the bottom. That is going to give you your horizontal asymptote, and the range is going to be from negative infinity to the horizontal asymptote number union horizontal asymptote to infinity. All right, to get the vertical asymptote, we know before that we've done vertical asymptotes, we have to factor. So we are going to factor the denominator and set each factor equal to 0. I have given you the problem f of x is equal to x plus 3 divided by x squared minus 9. I've factored the binomial, the difference of squares on the bottom to get x plus 3 times x minus 3. And to get the vertical asymptotes, I set each of those equal to 0 and solve. So this particular problem has two vertical asymptotes. There is an asymptote at x equal negative 3, and there is an asymptote at x equal positive 3. Two ways that you might see the vertical asymptote written here. You could see it as x is equal to positive negative 3, or you may see it written separate as x is equal to 3 or x equal negative 3. Okay, the domain is determined by the vertical asymptote, and I wanted, since this problem had two vertical asymptotes, I wanted to explain how to go about writing that. Remember that we're basically doing this like the number line from the left to the right. So the first one is always going to start at negative infinity. So we are going to have from negative infinity to negative 3, union negative 3 to positive 3, union 3 to infinity. So when there are multiple vertical asymptotes, you're going to have that extra union in the center showing the two asymptotes. Okay, and the last thing that I want to go over today is the definition of a hole. A hole in a graph is a point of removable discontinuity. Now, what does that mean? Discontinuity takes place when you have either vertical asymptotes or you have holes. So this graph we know is discontinuous at positive 3 and at negative 3 because those were our vertical asymptotes. But sometimes the vertical asymptotes will have that special name, holes. So what we do is we are going to factor just like we did before. We are going to cancel like we did before to get our final form of the equation. And to find the holes, we are going to take the canceled factor, which was x plus 3, and we are going to set that equal to negative or equal to 0 and solve to get x equal negative 3. So this problem in essence has the vertical asymptotes of x equal positive 3 and x equal negative 3, but because we canceled that factor out, that made one of the vertical asymptotes become a hole.